Okay, in section 6.3, we're taking a look at the Laplace transforms of sine and cosine, and then we'll be taking a look at some second-order differential equations, because we've seen sines and cosines showing up an awful lot there. Now, the formulas for the Laplace transforms of sine and cosine are formulas 2 and 7 on your formula sheet. You are responsible for being able to derive them. Okay. Now, if you're just using them, you'll have the formula sheet, but I could ask you to derive them. I could ask you that for any of the formulas on that sheet. I'm going to show you 4 different ways of deriving the formulas for sine and cosine. If I ask you to derive them on a subsequent exam, you can choose which method you want to use. Okay. Now, that's not to encourage you to just tune out on 3 out of the 4 and only learn 1. I encourage you to fully study and understand all 4 of the methods, because I think there's something valuable to be gained from each of those methods. But you can pick your favorite, and if I ask you to derive things on an exam, you can use that particular method. Okay, so I'm going to start with the Laplace transform for cosine of omega t. And I know just by the definition that that's the integral from 0 to infinity of cosine omega t times e to the negative st dt, which is the limit as b goes to infinity of the integral from 0 to b of cosine of omega t times e to the negative st dt. Okay. So the first method I'm going to show you is just using the definition and evaluating that improper integral. Of course, that's going to require integration by parts, because I have a product of 2 functions here, and they're very different. So I can't simplify the multiplication, and they don't work together to allow me to do a u substitution. So this is integration by parts. By the way, homework question 1 has you doing just exactly this, but for sine of omega t. Now, what I'm going to do as I work through this is I'm going to show you a sort of a nifty shortcut. It's a modification of a technique called tabular integration by parts. Tabular integration by parts is going to be where I keep a table of the u and the v prime that I'm using as I do integration by parts. This table is helpful because I'm going to have to do integration by parts more than once. So I'm going to just keep track of the functions that I'm working with in this table. Tabular integration by parts is generally useful when your u is a polynomial, because what's going to happen is you're going to repeatedly take the derivative of that function, and if you start with a polynomial, you'll eventually get to 0. Okay. Now, obviously, that's not going to happen here, because neither one of these is a polynomial. However, I can modify the tabular integration by parts that works for polynomials to work for a situation like this. So I'm going to show you that technique, which some of you may be familiar with and some of you may not. I'm going to just write up at the top, remind us what our formula is for integration by parts. That tells us that if I'm integrating from a to b, u v prime dt, that's equal to u times v evaluated between a and b, minus the integral from a to b of u prime times v dt. Okay. Now, remember, this basically comes from the product rule. If I took the derivative of the product of 2 functions u and v, I would get uv prime plus u prime v. So integration by parts is saying, hey, if you're integrating one of the terms from product rule, what you're going to get is the product minus the integral of the other term from the product rule. Okay, so the first thing I'm going to have to do here is decide which of these functions, the trig function or the exponential, is going to be my u, and which is going to be my v prime. Now, as we do that, we usually use this silly mnemonic device, this nonsense word liat. That just prioritizes which functions we choose for u. L stands for log, I don't have any logs. I stands for inverse trig, I don't have any inverse trig. A is algebraic, that would be powers, polynomials, rational functions, roots, anything I can build with those things. Don't have any of those. T is trig. I do have a trig. So I'm going to choose my u here is going to be cosine of omega t. And my v prime then will be e to the negative st. And I'm going to record that in my table. So the first time I'm doing integration by parts, I'm getting cosine omega t is my u, and e to the negative st is my v prime. Okay. Now, in order to do the integration by parts, I'm going to need to, of course, figure out what my u prime and my v are. I think what I'm going to do is actually slide this down to the bottom corner of the board so that I can continue my integration up here. So we said u was cosine omega t, v prime was e to the negative st. So u prime will be negative omega sine omega t, and v, just a quick w substitution here, will be negative 1 over s e to the negative st. Now obviously that's not going to be defined if s is 0. I can see if s is 0, that would just make this exponential factor 1. I'd be integrating cosine of omega t from 0 to infinity, and I know that diverges. So s can't be 0. And I can also see if s were negative, then this would be a positive exponential function that would be going off to infinity, and this integral would then diverge as well. In order to have this converge, I need s to be positive, so this is e to a negative power. So I'm going to need s to be bigger than 0. Now, I just discovered that in the table of Laplace transforms that's in your textbook, they actually omit that distinction. Now, I've made sure I added it to your handout that s is bigger than 0, but that's actually very important. If you're deriving the formula, it will be necessary that you state that. Okay. All right, and we'll need that eventually as we evaluate the limit. Otherwise, we'll get a divergent integral. Okay, so I'm going to also on my table record that my u prime was negative omega sine omega t, and my v was negative 1 over s e to the negative st. All right, so now let's write out what we're getting. So I'm getting the limit as b goes to infinity. And I'm going to need some brackets because I'm going to get two terms here. I'm going to get my u times v. Now notice the u times v is just this diagonal product right here, because that was my v that we had. So I'm going to get cosine omega t times a negative 1 over s, I'll just put that at the front, e to the negative st, and that's evaluated between b and 0, minus the integral from 0 to b of u prime times v. So that's negative omega sine omega t times negative 1 over s e to the negative st dt. Okay. Notice that what I have right here is exactly what I have in this row right here. So when we did the integration by parts, we got this product, that was our uv, so that's just evaluated, minus the integral of this product. And now this is going to be the new u times v that I'm going to use, because I'm going to have to obviously do integration by parts again, because I still have a product of a trig function and an exponential function. Now, if I were doing this without what eventually is going to be a shortcut, I would let those two negatives cancel. I would take this omega and this 1 over s, which are just constants, and I would factor them outside of the integral. I'm not going to do that because I kind of like that this is an exact match for what I have on this row. That's going to help me to see why this shortcut actually works. So I'm going to say, okay, I need to do integration by parts again. I'm going to just recycle the names u and v prime. I could put subscripts and say u1 and v1 prime and all of that. I'm going to just trust myself to remember that I'm recycling those symbols, and now we're doing it the second time. But now my new u is just going to be negative omega sine omega t, and my new v prime is going to be negative 1 over s e to the negative st. So that not only is this row the integral that I'm subtracting, but it becomes the start of a new problem. This is my new u, this is my new v prime. Okay. So my new u prime will be negative omega squared cosine omega t, And my new v will be 1 over s squared e to the negative st. Okay. Again, it's the same basic substitution that I'm doing to integrate and find an antiderivative of this. So I'll go ahead and write those down. So I'm going to have negative omega squared cosine of omega t, and then 1 over s squared e to the negative st. Okay, so let's write this out. I've got the limit as b goes to infinity of negative 1 over s cosine omega t e to the negative st evaluated between b and 0. Okay. Minus, now I'm going to have a new set of brackets here because I've got to use integration by parts again. So what I'm going to get is my new u times v. Notice that's this function times this function. So that's this diagonal product from my table. So I'm going to be getting negative omega sine omega t times 1 over s squared e to the negative st, and that's evaluated between 0 and b. I'm going to just sort of write at a diagonal here, minus the integral from 0 to b of my new u prime times v. But notice this is my new u prime and this is my new v. So what I'm integrating now is just the product that's in this third row. So negative omega squared cosine omega t times 1 over s squared e to the negative st dt. Okay, so we've got this lovely thing. Notice this integral right here involves a cosine of omega t and an e to the negative st. Now there's some other constants that I would be able to factor out, but that's actually the original integral that I was trying to evaluate. So this now gives me just a multiple of the original integral. So I'm going to be able to move this over to the other side and then solve for that integral. Okay. But if we look at all of this work and all of this mess, okay, it's basically all recorded right here in this table of values. The first time I did integration by parts, I got this diagonal product minus this integral. When I did this integral, I got this diagonal product minus this integral. Okay, so what's going to happen, let's take a look. This diagonal product, I'm going to keep exactly the sign that I have. If you take a look, this was a positive, this had a negative sign in it. That's exactly what I have right here. Okay, but then we were subtracting this integral. So because I'm subtracting that, this diagonal product is something that I'm subtracting, so that we're going to have that. Now, if I take a look at this integral, I'm subtracting twice, because this was the second time I did integration by parts. When I do integration by parts, I subtract the integral, but that was already part of what I was subtracting. So basically, I'm going to be adding this integral. Okay, this video's been going for a while. What I'm going to do is stop the video and continue this in the next video, but I'm going to erase all of this work and I'm going to duplicate it just using this table. That's where we'll pick up in the next video.